Now, before we go into how to do hydrate naming, I want to very quickly kind of talk about what a hydrate is. This is an example of one up on Smartboard. Magnesium sulfate, that should sound familiar to us. Magnesium +2, sulfate -2. Hey, what do you know? There's sulfate here. A magnesium's put in the middle. But when you look at this, what's unusual is water is surrounding it. A lot of ionic compounds exist more as what's called a hydrated salt, where water is loosely surrounding them. Hey, remember that time that we took those little Dippin' Dots, we put them in a weighing boat, left them out over the weekend, came back and they looked all liquidy? That was because they absorbed the moisture in the air, because that calcium chloride is more stable if it's all wet. Let's say it that way. Those blue crystals that we worked with earlier in the year, that we're going to work with again, CuSO4.5H2O, means that water's loosely surrounded that. I mean, if you think of the term hydrate, you might not think of that in terms of a chemistry class, but if you hydrate yourself, you add water. Some ionic compounds are more stable when they have water added to them. And that's basically what this top paragraph or two is talking about. Now, there's a term in the third paragraph in bold that's called anhydrous. That means without water. But what we have to do today is, because some ionic compounds are more commonly found as a hydrated compound than not, we have to learn this last type of naming for this semester. And then we're going to apply that in the laboratory setting for the next couple of class periods as well. So, halfway down to give you some examples. The good news is, I don't have to give you a new sheet or anything like that to figure this out. Take it part by part. The first formula on the sheet says BaCl2.2H2O. That dot represents that there's two waters loosely bonded to that BaCl2. Just name the part prior to the dot to begin with. So if I asked you to write down the written name of BaCl2, what would we call that? Ba is, and then chloride. So why don't you write down barium chloride on that line? Now, how many waters are loosely attached? 2. Look at your polyatomic ion sheet. Look at the very bottom right-hand corner where it gives you the Greek prefixes. What is the prefix for 2? Di. BaCl2.2H2O would be called barium chloride dihydrate. So not dye water, dihydrate. How about you do the next 2? LiCl.H2O, Na2S.9H2O. What I would say for the second problem is this is typically the one time that you do use the mono prefix. There is one water, let's say that there's one. So this is a monohydrate. So, second problem should have been lithium chloride monohydrate. Third problem should have been sodium sulfide nonahydrate. Let's look at the next problem. If I give you in writing, you should be able to figure out the formula. For example, strontium nitrate tetrahydrate. What I would say to myself is strontium, look at the periodic table, is a +2 charge. Nitrate, well, if it ends in ate or ite, I need to look at my polyatomic ion sheet. Nitrate is NO3 with a -1 charge. So what I would first do is figure out the formula of the strontium nitrate part. Cross and drop, or however we have to do it. And then after that, When it says tetrahydrate, there I should put a dot, a middle dot, and then 4, because that's the prefix for tetra, is 4, H2O. To hydrate yourself means to add water. To hydrate these salts means to add water. So strontium nitrate tetrahydrate would be SrNO3 2 4H2O. That middle dot represents a loose bond between water and that ionic compound. Since this isn't a great departure from what we normally do when it comes to naming, I'd like to give you a minute or two to try to fill in the rest of this front side when it deals with the naming, going back and forth. What we'll do then is we'll do the back side, where the back side is going to be going over mole conversions with this as well. And any type of naming that we do is stuff that we can measure out on a scale, which means not only can we not know the grams, we can know the moles of it as well. On the top of this sheet tries to break down how you would do a mole conversion. Again, what I would like to do is the first question with you, and then give you a chance to do a couple of questions after that. So, question number 1 says, what is the mass of 0.428 moles of zinc chloride hexahydrate? I'm actually going to give myself a little bit more room to work on this. It's always a good idea to write down what you're given. But one of the things I'm going to do, besides just writing down moles, I'm going to figure out the formula right now as well. So, zinc chloride, zinc's a +2, chlorine's a -1. That's ZnCl2. Hexahydrate, how many waters is that? 6. Now, what this question is asking for is to convert from moles to mass, which means grams. So that means grams is on the top, 1 mole is on the bottom. Just like when I introduced polyatomic ions to you, the tricky part is we have to figure out the molar mass. Otherwise, this is the same type of conversions we've always done. Okay? If I look at the periodic table for zinc, was that 65.41? I look at the periodic table for chlorine, 35.45. Decker, why don't you have these memorized by now? Okay. But there's 2 of them, so I'm going to multiply by 2. Okay. Now, a middle dot in a math class means multiplication. A middle dot in a chemical formula does not mean multiply these masses together. That middle dot just represents that it's loosely bonded together. Typically what you would do is you'd add the zinc and the chlorine to get your mass. But we also have to add to that the mass of the 6 waters. Now, here's what I prefer to do. Hydrogen's 1.01, and there's 2 of them. Oxygen's 16. In general, I just remember that water is 18.02. Because I have 6 waters in my formula, I'm going to multiply that by 6. That way, I don't have to do 12 hydrogens and 6 oxygens and add all together. I almost treat water as its own element. But it's always going to be 18.02 with these, so there's another one that you can remember, Decker. Good? Yeah. Okay. So I multiply that out to carry the 1, and then what is that, a 48? So there's an 8, there's a 108.12. So I'm going to add my 108.12, my 70.9, my 65.41. And hopefully my answer key is correct when I write this down. 244.43 grams. I think so. So now you do your mole conversion as you normally would. This times that.
I think it's 2 4.
Okay, so this times this. 3 sig digs because of this right here gives me 105 grams. So your mole conversion is no different than before. It's figuring out the molar mass that's the tricky part. Okay? So what I'd like you to do, and probably based upon time, we're only going to do one question on here right now. The good news is the homework isn't on hydrate naming and mole conversions. Let's have you try to do number 2 right now, where number 2 says how many molecules, that means we're going to have to use Avogadro's number at some point, would 11.68 grams of copper 2 sulfate pentahydrate be? I would definitely figure out the formula of copper 2 sulfate pentahydrate as my first step. Again, if we started with grams and we wanted to get to molecules, our step 1 would be dividing by the molar mass, which a lot of you I think are figuring out right now. Our step 2 would be multiplying by Avogadro's number. So copper being 63.55, sulfur being 32.07, 4 oxygens is 64, 16 times 4. Add that up with the 5 waters, which each water is 18.02 times 5 would be 90.1. All that added together would get you 249.72. So again, I divide, I multiply, 2.816 times 10 to the 22nd molecules is what I would get for that problem. Now again, there's 2 more problems on that worksheet. However, we need to spend a little time introducing our last topic, and it shouldn't take a lot of time today, but our last topic, which is percent composition. So we are moving on to percent composition. And if you think about what it means for percent composition, it's how much makes something up. Now this could be in chemistry or this could be outside of chemistry. Again, percent composition is take the total of whatever you're looking at and take whatever specifically you want to look at divided by the total. We're going to do the same thing here. Percent composition is our last step in this compound unit, because what we're going to do is we're going to look at what is the percent of each element that makes up a compound. Remember that some elements have a larger mass than others. So we cannot base this on the ratios from the formula itself. We have to base it upon more kind of work with our periodic table. Now that handout you picked up on the way in, oh boy, there's a big long paragraph on the top. Let's skip it. There's a nice sample problem in the middle. Let's skip it for now. Let's look at question number 1, or letter A rather, on the very bottom of the page. It gives you copper 1 oxide. What we are going to do right now is we are going to calculate the percent of copper and the percent of oxygen in this compound. In order to do that, we need the formula for it. So why don't you take 20 seconds. And there's only 2 elements to this thing, so it shouldn't take too long. Let's take 20 seconds to figure out the formula for copper 1 oxide. The 1 does not stand for how many, it stands for the charge, which is why the formula is Cu2O. Now, if I want to figure out the percent of each element in that compound, here's what I do. I look on the periodic table. Copper is 63.55. And there's 2 of them in the formula. That gives me 127.1. Oxygen is 16 on the periodic table, and there's only 1 of them. I don't know if I have to really write times 1. Gives me 16. Let's add the 2 together. 143.1. I have the mass of each part and the total mass. Then from there, and I'll show you this is a different step by just simply using a different color, I'm going to take the mass of the part divided by the total for each. Now this would give you a decimal value. However, multiply by 100 to express it as a percent. I'm not going to show that work, and I hope that you realize you don't have to show that either. It's assumed that you understand decimal to percentage. Since this is a percent composition problem, that's all you have to do. Some students are going to ask about sig digs of, hey, should I report with 4 for this one and only 2 for this one? We typically tell students that since percent composition, if you're using the periodic table, has nothing to do with a measurement as much as just the periodic table values, let's just be consistent with the number that we use. I often like to go to the tenths place. So for example, this would be 88.8%. This could be 11.2%. There's a reason why I didn't think we needed to spend a lot of time on percent composition. This is basically all it is. Heck, I could do this with lab data. I could say a certain compound took 5 grams of copper and 6 grams of oxygen to combine. What's the percent of each element? Then you could take 5 divided by 11 and 6 divided by 11 to figure out the percent. But if we're just giving you the formula, that's what we would do. Letter B. What's the formula for hydrogen gas? H2. It's one of our diatomics, right? Hydrogen has a mass of 1.01. There's 2 of them in the formula. 2.02 is the mass due to hydrogen. Since that's the only element, I'm going to divide it by that. This is a weird problem on this worksheet. I've just mathematically proved that 100% of hydrogen is hydrogen. Would you flip to the back side?